We're going to do a little bit of review of exponent laws quickly before we get into exponential functions. So looking at this, we talked about positive integers on an exponent. So a positive integer, something like having 3 to the exponent 3, just translates into 3 times 3 times 3. Okay, we're just multiplying by the number as many times as the exponent is there, is the times that we see the number. Okay, a 0 exponent always equals 1. No matter what that number is, it could be A, it could be 3, it could be 48 billion. It's always going to be equal to 1. A negative exponent switches the side of the fraction. So if it's on the top, it goes to the bottom. Bottom goes to the top, and then becomes positive. So if we had like 3 to the negative 2, that's equal to 1 over 3 squared. Okay, and we did a bunch of examples in the first note for that. Recognize also that this is true. So we talked about in the last note that the third root of something, or the cubed root, is the opposite of cubing something. You can also take it to the negative exponent because it's going to be the same thing. It will also get rid of it. All right. Or actually, sorry, it will make it equal to 1. It won't get rid of it per se. It will make it equal to 1. So exponent laws to numerical and variable bases. So if we have the same base, what all this means is if the base is the same, we can apply these laws. Okay, now we've done these laws a few times before, so I'm not going to spend a lot of time on them. But if we had something like x to the n times x to the m, where the two bases are the same, all we have to do is add the exponents. Okay, the division is the same. So if we had x to the a divided by x to the b, in this case, we're just subtracting the exponents. Whoops. Power of a power, we're going to multiply. So we'll change the variables again. If we had x to the, let's call it g, and the, I don't know, k. I don't want to use L, it's too confusing. Then we'd get something like this. gk, or g times k. And the last thing, a simplified expression always has positive exponents. So if I ask you to simplify, you need to have positive exponents. Okay, so a few examples. So if I have common base, so I've got a b and a b, it's asking me to multiply them. All I have to do is add my exponents. 2 plus 4 is 6. Same thing for the second question. Okay, it looks a little bit different because I've got a negative, but I'm just going to do negative 8 plus 5. I get b to the negative 3. Well, that's not simplified. I need to change that to 1 over b cubed. Okay, power of a power. I'm going to multiply my exponents. So 2 times 3 is 6. Subtraction. Okay, because we've got a division, still common base. It's going to change to b to the negative 1. And that just equals 1 over b to the 1, or just b. Okay, power of a power again. I'm multiplying my exponents. Okay, and I hope that this stuff is review. We've done this a few times in the past. Okay, all I'm doing is looking at what the operation is and is the base the same. If it's multiplying, I'm adding them. Okay, the next one here, it's multiplying. So 5 plus negative 3 is 6 squared, and 6 squared is 36. This next one's a little bit harder. We've got 2 minus negative 1. So 2 minus negative 1 is actually 2 negative, so it's going to be 2 plus 1. And negative 3 cubed is negative 27. Negative 3 times negative 3 is 9. And negative 3 times 9 is negative 27. Okay, a question like this, we can just work through it slowly. We can do the top first, then in the bottom, and then put them together. Okay, so we've got x squared and x to the negative 6. So that's going to be x to the negative 4 over power of a power. It's going to be x to the negative 6. I'm going to write beside because I've run out of room here. We do negative 4 minus negative 6, or negative 4 plus 6. We get x squared. Okay? Slowly working through it step by step. Looking at this last one, it says evaluate. I'm going to use my exponent laws first and then substitute in so that I only have to look at the variables once. Okay, so this 4 has to go to each part of my term. So it's going to be 2 to the 4. So 2 times 2 is 4, times 2 is 8, times 2 is 16. I'm just going to write 16. Then I'm going to have a to the 8, b to the 3, or sorry, b to the 12. Okay, and I'm going to get rid of those so you can see it a little better. Now I'm going to substitute in. So it's going to be 16, 1 to the 8, negative 2 to the 12. And I've got to write it beside here because I've run out of space. But 2 to the 12 is going to be 4,096 times 16. It's going to give us 65,536. And I don't have to do anything with the 1 because the 1 is going to just be equal to 1. Here we've got negative 3 and 4. So I've got to just look at my a's first. So this just becomes a to the 1, or a. Then we've got b to the 6, because if I don't have an exponent, there's actually a 1 there, and 1 plus 5 is 6. So now I get 1 and negative 2 to the 6, and 2 to the 6 is going to give me 64. Okay, and that's going to be positive. Now this one's a little bit more difficult, but it's only difficult because of all of the numbers and stuff. But let's just look at the top, just look at the bottom, and then put them together. Negative 2 times 8 is negative 16. Look at the numbers first. A and a squared is going to be a cubed. B to the 5 and b to the 2 is going to be b to the 7. All divided by 4 squared, because I have to do the squared on the 4, is 16. A squared. And then b to the 6. Okay, now 16 divided by 16 is just going to be a negative, because that's just going to be negative 1. A, b, 3 minus 2 is 1. 7 minus 6 is 1. So this is negative 1 times negative 2. So that's just going to be equal to 2. It's a lot easier if you substitute in at the end for a question like that. All right, last one. So this is something that we did, or this is out of your notebook. So computer power has been doubling approximately every 2 years as more and smaller transistors have been integrated to build better computer chips. It's actually probably an old stat. It's probably faster now. We've got our formula. The number of transistors equals 45,000 times 1.4 to the n, where n is the number of years since 1974. Determine the transistors in a computer for each of these years. Well, the first one says from 1974. Well, what that means is that n is 0, because from 1974, no years have passed to get to 1974. So we have a 0. So this is 4,500 times 1, because anything to the exponent 0 is 1, and we always have to do BEDMAS, so we're doing 1.4 to the 0. So in the year 1974, we had 4,500 transistors. Now let's go 2013. So the way I'm going to do this is my n, I'll write it over to the side here, n is going to be equal to 2013 minus 1974. So 2013 minus 1974 is going to give me 39. And now I'm just going to sub that in. So we've got 4,500, 1.4 to the 39. Remember, you have to do BEDMAS. So you have to do 1.4 to the 39 first, and then times it by 4,500. So when you do the first part, you should get about 500,000 times 4,500. Now you're getting 2,250,121,167 transistors. Okay, obviously that's probably getting a little too big, but you never know. All right, and here are some questions out of the textbook for that part of the chapter.